Good morning. I'm Allison Hahn, Program Manager for the Light Water Reactor Sustainability Program. I will be briefing you on 6 separate work scopes today. These work scopes are all open to university-led researchers. With that, however, we do encourage collaboration with other organizations, including industry and national labs. So, as an overview for the LWRS program, you can see here the goal is to enhance the safe, efficient and economical performance of the existing fleet while also extending the lifetime of these reactors. Some of you may be familiar with the LWRS program, and this goal has recently changed in this past year with the successful submittal of 2 SLR applications. We are kind of revamping this program. We will still be looking at the materials issues for 60 to 80 years, but we're also looking at the economic challenges that the current fleet is facing. So looking at the focus areas, we still include materials research. The old II&C pathway is now plant modernization, research and development. Then we also have the risk-informed systems analysis pathway, which was formerly known as the RISMIC pathway. The work that was previously performed in the reactor safety technologies pathway is now wrapped up into that risk-informed systems analysis. So the first pathway within LWRS is that materials pathway, whose goal is to understand and predict long-term environmental degradation behavior of materials in nuclear power plants, including detecting, characterizing, and mitigating aging degradation. The outcomes in this pathway will provide key input to both regulators and industry on the operational limits and aging mitigation approaches. The next one, plant modernization area, will work to address nuclear power plant economic viability through innovation, efficiency gains, and business model transformation through digital systems, through digital technologies. The intended R&D products here will enable modernization of plant systems and processes while building a technology-centric business model platform that supports improved performance at a lower cost. In the RESA area, we are performing R&D to support decision-making related to economics, reliability, and safety by providing integrated plant systems analysis solutions to enhance the economic competitiveness of the existing fleet. The R&D products in this pathway will be used to optimize plant economic performance and safety by incorporating plant impacts, physical aging, and degradation processes. And then lastly, our systems analysis and emerging issues pathway. This is our blue sky area. We're investigating a number of activities in this area with the overall goal of reducing operating costs and/or increasing revenue. Our plant modernization pathway is working to significantly reduce the technical, financial, and regulatory risk of I&C modernization by demonstrating and validating new technologies and operational concepts at host nuclear plants, by providing the technical basis reports to support long-term planning, procurement, and regulatory submittals, and by providing guidance for full-scale implementation and communicating those results to other nuclear power stakeholders. We're not simply trying to replace analog with digital technologies on a like-for-like basis. Rather, we are working with asset owners and vendors to deliver greater functionality, higher reliability, improved situational awareness, and a technology base that is more affordable and sustainable over the life of the plant. We are working with industry through an industry working group, which includes 13 nuclear utilities and EPRI, to identify the greatest challenges and opportunities where R&D can have the greatest impact. So in this plant modernization pathway, we have 2 work scopes this year. The first is digital I&C qualification. This area continues to be a major impediment to addressing the reliability and obsolescence issues in legacy analog I&C systems for the operating light water reactor fleet. In particular, this issue of digital common cause failure has been difficult to address and has been the reason some nuclear plant operators have deferred upgrades of these critical plant systems, opting rather to maintain them with costly engineering and maintenance efforts. To enable the light water reactor fleet a path forward with digital upgrades, a qualification method to address these CCF needs to be available. There are 2 proposed qualification methods that require further investigation. The first is testability, and the second is the elimination of those CCF triggers. First, testability, that exhaustive 100% testing of certain digital devices accounting for all combinations of inputs and internal states to ensure there are no digital defects. And then second, the elimination of those CCF triggers, ensuring that any latent digital defects are not concurrently triggered in multiple digital functions that are assumed to be independent, such as those redundant safety systems. The outcomes of this research would be to develop qualification methods and processes that would potentially address the technical and regulatory aspects of digital qualification with regards to digital CCF. The next one is equipment condition monitoring. Equipment monitoring is one of the main contributors to maintenance costs for nuclear power plants. Whether it's or prognostics, condition monitoring is mostly based on manual efforts to collect and analyze measurements using conventional sensors and methods. Decision-making is driven by a combination of periodic inspections based on vendor specification, industry standards, and human experience. A need to automate the phases of data collection and analytics-based decision-making has emerged to reduce workforce cost, optimize the maintenance activities during normal operation and outage operations conditions, maximize the maintenance activities value, and reduce risk and human errors. In line with the vision to automate the condition monitoring process, research will focus on identifying novel sensors, automation technologies, and data analysis methodologies for optimized condition monitoring in nuclear power plants. There are two areas that provide some challenges in this area. The first is seamless data integration, which includes identifying and installing technology that will gather, integrate, communicate information, and integrating multiple databases that don't currently support a seamless data environment. The second is improved data analytics, which is tied to platforms that have small algorithm libraries that won't support a meaningful switch to a risk-informed maintenance program in the near future. And equipment instrumentation and monitoring does not always provide information to support analysis of all failure mechanisms. The outcome of this research will help the light water reactor fleet drive down the costs of maintenance by providing a scalable and adaptive data infrastructure solution needed to enable implementation of a risk-informed maintenance program. Speaking of risk-informed, our RESA pathway in the light water reactor sustainability program provides tools and methods to inform nuclear power plant margin management decisions with a focus on improved economics and reliability. These tools and methods were developed throughout the last 7 years with a focus on coupling risk assessment, that probabilistic, and systems margin quantification, or that deterministic, to achieve very accurate modeling and representation of margins for the long-term benefit of nuclear power plants. The figure on this slide illustrates the strategy to achieve the stated goals. We demonstrate the RESA methodology by focusing on industry pilot demonstrations that have the greatest positive economic impact to the current fleet, which is the quadrants on the right there, while sustaining high levels of safety, which is the bottom right quadrant. The term use case refers to the RESA methodology implementation strategy in coordination with nuclear industry organizations in pilot demonstration projects addressing key issues relevant to nuclear power plants. There are 4 broad use case categories supporting challenges the nuclear fleet faces today. The first is enhanced resilient plant systems, using modeling and simulation to demonstrate how innovative concepts can be combined together to further enhance operational and safety performance. For example, integrating the introduction of advanced fuel concepts, the ATF fuel, with enhanced operational strategies such as flex operations, and innovative cooling systems concepts such as the Terry turbine extended operating band for BWRs. Combining these strategies may present cost-saving opportunities to a nuclear power plant and should be analyzed in an integrated manner. The second is cost and risk categorization, which is the application of the RESA computational framework that combines physics, risk, and cost information to enable risk and cost-based decision-making in optimizing maintenance activities to achieve the greatest cost efficiency through 5069. Third is margin recovery. This will apply risk-informed, multi-scale, multi-physics, high-fidelity simulation tools to investigate conservatisms associated with an existing plant design process and provide a path to recapture margins, reducing operating costs and or gaining operational flexibility. And then lastly, our market economics, quantifying the economic challenges of the existing fleet. Market data for the existing fleet can be used to understand current markets and propose viable solutions to address revenue shortfalls. So within this area, there are also 2 work scopes. Use of integrated PRA and mechanistic tools to accelerate deployment of advanced technologies to LWRs is the first scope. This scope will be to develop and apply an integrated PRA and mechanistic simulation framework to reduce the time, cost, and uncertainty associated with developing, demonstrating and deploying new nuclear technologies and plant operational strategies. The resulting integrated evaluation framework should enable plant system configuration variations to be studied with speed and precision, including detailed risk and benefit assessments of introducing these advanced nuclear technologies into current plants to achieve both safety and operational performance enhancements. Proposals that combine the analysis methodology development and experimentation into a unified approach to address key technical and economic challenges are strongly encouraged. The second work scope within the RISA pathway, risk-informed asset lifecycle management and maintenance optimization. This scope is seeking research proposals designed to reduce nuclear power plant operational costs by identifying plant asset management data that is needed to develop tools for risk-informed insights that can improve plant asset management. Methods and tools will be developed to allow risk-informed integrated business case assessments for SSCs that can be more effectively and efficiently address equipment performance. This may include the use of improved data analytics with a focus on their use and management of data that are currently available. Proposals should address the development of advanced predictive and data analysis models integrated with the Raven statistical framework, the integration of results in a coherent plant asset management framework, and may also consider how to use the results to assist in ranking major capital refurbishment and replacement of SSCs for the lifetime of the plant, to risk-inform the capital improvements that includes assessment of expected useful life. The methods and tools will be used to develop an optimized schedule for capital replacement or refurbishment of major equipment for extended operating plants, or extended plant operations. The next pathway is our materials research pathway. This pathway has been focused on four main principal areas of activities. Reactor metals, which includes RPV steels, mechanisms of IASCC, and SCC initiation of nickel-based alloys, as well as the effects and impact of the environment on materials performance. Concrete degradation, which includes radiation and environmental-induced damage, ASR and NDE techniques. Cable systems, to include mechanisms and modeling of cable insulation aging and degradation, and NDE techniques to characterize cable damage and remaining useful life. And lastly, mitigation technologies, which include advanced weld repair techniques and potential advanced replacement materials. Research in these principal areas addresses the scientific research gaps identified in the DOE and NRC expanded materials degradation assessment for extended reactor operations, and are prioritized based on industry needs as identified in EPRI's Material Reliability Program document. To address the scientific research and development gaps for extended reactor lifetime requires a multi-directional approach that includes experimental testing, modeling or simulation, and the examination of harvested materials. The R&D products developed from this program will be used by utilities, industry groups, and regulators to inform operational and regulatory requirements for materials and reactor systems, structures, and components subject to long-term operating conditions, providing key input to both regulators and industry. Again, there are two work scopes in this area. This scope seeks proposals that will develop rapid experimental techniques that, when coupled to multimodal imaging and compositional analysis methods, can provide an assessment of concrete tolerance to environmental degradation. Degradation modes of relevance include, but are not limited to, irradiation damage resistance and chemical inertness at superambient temperatures in the presence of moisture. Existing protocols for degradation assessment, such as those based on ASTM standards, are unsuited for assessing concrete's tolerance to degradation in such extreme environments. Mosaic is an integrated computational materials engineering software we expect applicants to use to inform and analyze their novel experimental accelerated degradation techniques. The second work scope, modeling of helium bubble development during welding of irradiated metal alloys. Helium is generated in nuclear structure materials from reactions between the thermal neutrons and boron impurity or through two-step reactions with nickel. During repair welding, helium will diffuse and coalesce at grain boundaries and embrittle the metal, resulting in helium-induced cracking by welding residual stress, with as little as a couple of atomic parts per million helium concentration in welded metal. Key factors that affect irradiated material welding quality are high temperature and tension stress. This call seeks the development of a comprehensive model that addresses the boundaries for weld repair of irradiated materials based on heat input, the welding technique, and material conditions, the helium amount and microstructure of that base metal. So that concludes my presentation. Luckily enough for all of you beautiful people, we have our technical leads available on the line to answer any of those technical questions you may have.
Is there a limit to the number of proposals that can be submitted? So there is a standard set of rules that can be found in past FOAs if you're curious. This one won't be released until later in August. There are application submission limits for university principal investigators. That's 6 applications total with 3 as lead PI. And those are pre-applications. Yep, thank you. I just got some clarification in the room. Allison, starting in RC 10.1, is reinforcing steel considered a concrete constituent of interest for this work scope, or just the cementous material and aggregates?
I'll defer to Keith.
The cement is a little bit more important right now. We have within the program some work with the NRC on the kind of rebar subject. We're a little bit more interested right now in the concrete makeup rather than, excuse me, the rebar itself, or rebar concrete interaction.
In RC 10.1, is ASR still being considered?
Yes. So we are very interested. Proposals don't have to be limited to either radiation damage effects or ASR. Either subject is very valuable to us and is relevant to the work that we're doing within the program. So yes, alkali silica reaction is a subject of interest.
Would DOE provide access to radiated concrete, or would proposers be responsible for sourcing this material?
I think we'd be open, and you can certainly work with DOE people or you know, that have access available to irradiated concrete as an option. So yes, it would be something that is a relevant, good proposal would be of interest to DOE researchers, and I would be in favor of making resources available to them in terms of materials.
For RC 10.1, is modeling of multi-ion diffusion to predict initiation and progression of reinforcement corrosion and full coupling with crack-initiated mechanisms like ASR and freeze-thaw considered as important?
Can you repeat that one more time? You broke up a little bit on my speaker.
Is modeling of multi-ion diffusion to predict initiation and progression of reinforcement corrosion and full coupling with crack-initiating mechanisms like ASR and freeze-thaw considered as important?
It is an issue. It is an important issue. I think it could be applicable to this work scope.
Moving on to RC 9.1, according to last year's NUP awards, there was one project analyzing coping time and cost analysis of accident-tolerant plant design based on probabilistic risk assessment. Are you looking for a different aspect for RC 9.1?
Yes. Not looking for a different aspect, but emphasizing the combined strategies that you may have with looking at fuse and accident-tolerant fuse as a systems components with other systems components. So the combination analysis of fuse and accident-tolerant fuse are included in combination of other advanced strategies. That's what we're looking for. The application of multi-physics tools that both address the deterministic and also the probabilistic areas combined and integrated for the benefit of the plants.
For RC9, will DOE provide access to deterioration and maintenance data, or is it the responsibility of the PIs to collect such data?
The intention is for the PIs to provide a data set or a data bank that they would like to work on, and even partner with industry to acquire the data.
For RC 9.2, maintenance optimization focuses solely on capital refurbishment / replacement, or is there also interest in optimizing routine maintenance activities?
Both. As you notice, there are three topics of interest there: capital refurbishment, existing components, maintenance and optimization, and also looking at the lifetime of components throughout long-term operation.
Moving on to RC 8.2, what specific conditions are you looking to monitor?
So we're looking at all aspects of operations. So at power, during shutdown conditions, looking at getting process information, structural information, all feeding into what would support operations and maintenance activities.
Keith, moving back to RC 10.1, would coupling between ASR and irradiation effects modeling without specific testing be considered as appropriate for RC 10.1?
Yes, it can be. There is some indications, though not really well established, that there may be some interactions between irradiation damage and ASR, or ASR further influenced by irradiation damage. So there would be an interest.
This last question is one that I'll answer. Will the application process require submission of white papers this year, or will it go directly to full proposal? And the answer to that question was answered yesterday morning during the overview. The intention is to move back to the normal NUP process, which has a pre-application component that's typically due 6 to 8 weeks after FOA release, and a full application component that will have invited and uninvited applications based on the results of the pre-application process. Okay, Allison. Oh, we have one more question. Will RC 10.2 include validation of modeling by actual welding of irradiated materials?
It would be ideal to have an experimental component of at least some level to validate model predictions, yes.
Okay, now we have some more questions for me. So, in RC9, is an extreme natural event of interest in optimal maintenance planning?
Yes, extreme events is being part of the activities that are being considered, particularly with respect to categorization of equipment.
Okay, I believe that is our last question. If you do have further questions or want to discuss further iterations of these topics, please contact Allison or one of the technical points of contact. Those are available on neup.gov underneath R&D, the R&D tab, technical points of contact. So please reach out to them if you have any further questions about the scopes